Hello everyone, I'm Xiao Mao from MIT, and today I'll talk about my paper titled Breaking the Cubic Barrier for Unweighted Triadic Distance. For two strings S and T, their added distance is defined to be the minimal number of insertions, deletions, and substitutions needed to transform S into T. It is a measure of the similarity between two sets of linearly organized data. However, in some applications, such as in computational biology, structured data analysis, and compiler optimization, data sets have hierarchical structure instead of linear structure. For these data sets, we need a better measure of the similarity called triadic distance. For two trees, T1 and T2, the triadic distance between T1 and T2 is defined to be the minimal number of operations needed to make T1 and T2 identical. More precisely, trees are rooted, children are ordered from left to right. Each node has a label from a certain alphabet sigma. In this paper, we assume that the alphabet can be of the same size as the input tree, or n. In each operation, we can relabel a node, delete a node v, and make the children of v the children of its parent. Operations can be done on either tree, and as we shall see, this makes sure that no insertions are needed. Here is an example. In this example, we are given two trees, T1 and T2. In the first operation, we delete a node from T1. In the second operation, we relabel a node from the resulting tree. In order to change this tree into T2, one would like to use the insertion operation. However, it was not annulled. We do annul operation on T2. So instead of doing an insertion, we do a deletion from T2, and this achieves the same effect. After this operation, the two trees are made identical. Since we have used three operations, the triadic distance between the two trees is equal to 3. There has been a line of research on triadic distance, stemming from the seminal work by Tai in 1979, which gave an algorithm that ran in n to the 6th power time. Here, n is the size of the two input trees. The state-of-the-art algorithm was due to Domain, Moses, Bachman, and Wyman in 2007, and it was the algorithm that ran in cubic time. Interesting enough, the last three algorithm actually use the same DP scheme. On the lower bound side, Freeman, Gorbaczewski, Moses, and Wyman showed in 2019 that under the APSB conjecture, no truly subcubic algorithm is possible for the weighted case. In my work, I made a breakthrough by showing that a truly subcubic algorithm is possible for the unweighted case by showing an algorithm that runs in n to 2.9546 times. Here is the outline of this talk. Firstly, I'll talk about the traditional DP scheme by Zhang and Shasha and its limitation. Secondly, I'll talk about a new cubic DP scheme. And finally, I'll give a sketch of how we can break the cubic barrier based on this new DP scheme. Although we define triadic distance on two trees, T1 and T2, it is easy to extend the definition to forests. Now we consider how we can compute the triadic distance between two forests, F1 and F2. In order to do this, we consider matching the rightmost roots RF1 and RF2, labeled in green circles. There are several cases we need to consider. The first case is that when RF1 and RF2 are matched to each other. In this case, we update the triadic distance using three parts. The first part is the blue part, the second part is the red part, and the final part is the green part. And for the green part, we can see that this is equal to 1 if the symbols on the two roots differ, and 0 if the symbols agree. Case 2 is if RF1 is not matched. In this case, we delete RF1 and match the remaining part. We update the journey distance using 1, which is the cost of deletion, plus the edit distance between F1 with RF1 removed and F2. The final case is if RF2 is not matched, and this is similar to the second case. This is symmetrical. In this case, we update the journey distance using 1 plus the edit distance between F1 and F2 with RF2 removed. What is the complexity of this procedure? In order to analyze the complexity, we define subforests. For a forest F, a subforest of F is any forest we can get from repeatedly removing the leftmost or the rightmost root from F. One might assume that we do not need to consider removing the leftmost root, since in my description of the algorithm, we only considered matching the rightmost root of the two forests. However, it turns out that in the analysis of the algorithm, we do need to eventually consider removing the leftmost root. Fortunately, even if we allow removal from either direction, we can prove that the total number of subforests we can get is quadratic. Therefore, the complexity of Zhang and Shasha is equal to the number of pairs of subforests, which is O(n) to the 4th power. We just had a DP recurrence by considering the rightmost root. And it is easy to see that we can design a similar DP recurrence by mirroring the DP recurrence and consider the leftmost root. The n-cube logging algorithm by Klein does exactly that, and it chooses the direction in a clever way to achieve this running time. The cubic algorithm by domain Moses Wassman and Wyman chooses the direction in the optimal way and achieves a cubic running time. But on the other hand, it means that there's no improvement possible by using an even more clever way to do this DP scheme. So why did Zhang and Shasha scheme fail to reach truly subcubic, as evidenced by the main adult result? This is because no matter how we choose the direction, we can always easily modify the scheme to solve for the weighted case. All we need to do is to change the 1 in our DP scheme to the cost of deletion and replacement. However, we already know that the weighted case is FEXT hard. It means that if there were a truly subcubic adaptation of Zhang and Shasha, it would imply a truly subcubic algorithm for FEXT, which is unlikely. What does this actually tell us? It tells us that if we want a truly subcubic time algorithm for the unweighted case, we will need a new DP scheme that can exploit the fact that the operations are unit cost. That's exactly what my new DP scheme does. It works on the inverted problem of similarity. For two forests F1 and F2, the similarity between F1 and F2 is defined to be the size of F1 plus the size of F2 minus the edit distance between F1 and F2. Minimizing edit distance is therefore equivalent to maximizing similarity. A good visualization of similarity is to visualize it as finding a max weight matching between the nodes of the two input forests, where the max nodes contribute 1 if their symbols differ and 2 if their symbols agree. In this example, we are given 2 trees, and 5 pairs of nodes are matched between them, among which one of them contributes 1 since their symbols differ, and the other 4 contribute 2 since their symbols agree. Therefore, the total weight of this matching is 9. And we can show that this is actually the max weight matching between them. Therefore, the similarity between these two trees is equal to 9. Next, I'll give a new perspective on the subforest and relate it to intervals. In order to do this, we define the extended by-order traversal sequence. To get this sequence, we pre-order traverse the tree. Every time we enter a node or leave a node, we attach the node to the sequence. We can see that each node appears exactly twice in this sequence, and for a node x, we let L of x and R of X to denote the index of the first and the second occurrence of this node. The subforest T of the interval L to R is defined to be the subforest we can get by removing all nodes F, where at least one of its occurrence is not inside the interval L to R. Here I give an example of a tree, as well as it is extended by all the traversal sequence, and the example of a subforest in red. The subforest F equals T of the interval 3 to 15, contains exactly the red node. For example, it contains the node 7, since both of the occurrences of 7 is inside the interval. On the other hand, it does not contain the node 2, since only one of its occurrences is inside the interval. And our definition dictates that both of the occurrences have to be inside the interval. We also know that this definition is not a one-to-one mapping, meaning that different intervals can correspond to the same subforest. Now we introduce our new DP scheme based on these two definitions. For three forests F1, F2, and F, if we consider the concatenation of F1 and F2 denoted by F1 plus F2, suppose we want to compute the similarity between F1 plus F2 and F of the interval LR. How can we do this? It turns out that this is equal to the maximum over all the indices K in L to R. The similarity between F1 and F of the interval L to K, which is the red part, plus the green part, which is the similarity between F2 and F of the interval K to R. And I have given a visualization of how this DP scheme works. Basically, it enumerates to all the possible ways we can match the red part and the green part by letting K be all the indices between L to R. Let the input trees be T1 and T2, both of size n. For a subforest F of T1, we can define a similarity matrix S of F, where the SIJ entry is equal to the similarity between F and T2 of interval I to j. The similarity matrix S of F1 plus F2 is equal to the max plus product of S of F1 and S of F2, as evidenced by the DP occurrences we have given before. Therefore, we can use the bottom to top DP that computes the similarity matrix of the subtree U for each node on U on T1. And this uses ON max plus product. However, max plus product takes cubic time in general. And this a naive implementation of this DP scheme only reaches the running time of ON to the fourth power, which is obviously not optimal. In order to improve this DP scheme, we would use two important properties of similarity matrices that arises from the fact that the operations are unit cost. The first property is that the similarity between the forest F and the tree T2 is no greater than 2 times the minimum of the size of F and the size of T2. This is because similarity is basically the weight of a matching, and the total number of match pairs is obviously no more than the minimum of the sizes of the two input trees. And this is obviously no greater than 2 times the size of F. The second property is, if you are given an interval LR and another interval L prime to R prime that contains this interval, then the similarity between F, the forest F, and T2 of L prime to R prime is no less than the similarity between F and the subforest T2 of L to R. This is because T2 of L prime to R prime is going to be a superforest of T2 of L to R. What does this mean for the similarity matrices? Property 1 would mean that A similarity matrix always has entries bounded by 2 times the size of the forest F. The second property means that the similarity matrix is always row monotone and column monotone. In the top right corner, I have given an example of what the similarity matrix might look like given those two properties. There are two really good consequences of this property. The first consequence is that the similarity matrices are compressible. S of f of size n squared needs only odd n times the size of f entries to represent. What are the entries needed? We only need the first occurrences of each number between 0 and 2 times the size of f for each row. Since there are n rows in total and O the size of f numbers, there are only O n times the size of f entries needed. And in the top right corner, I have highlighted the entries needed to represent this matrix. A compatibility means that we have a faster way to do max plus multiplication, which is exactly what we wanted. If the compressed forms of S of f1 and S of f2 are known, we can compute the compressed forms of their max plus product in O(n) times the size of f1 times the size of f2 times. We have shown that max plus product now has a much better running time. What does this say for our total complexity? We can prove that with this improvement, the total time complexity has decreased from O(n) to the fourth power to cubic. However, what we really wanted is an algorithm that beats the cubic running time. How can we improve this to truly subcubic? In order to do this, we use a decomposition scheme. Instead of doing O(n) transitions one by one, we decompose the transitions into O(n) over d blocks of transitions of the following two types, for some parameter d slightly smaller than the square root of n. The first type of transition is a transition from some forest f1 to a super forest f2 of f1, where the difference between the sizes of the two forests is no greater than OD. The second type of transition is a transition from two forests f1 and f2 to their concatenation f1 plus f2. As we have shown before, this is equivalent to taking their max plus product. For the first type of transitions, with some extensions of the ideas used in the cubic algorithm, we can achieve a running time of O(n) times d cubed. And therefore, the total amount of time we need for the first type of transition is equal to O(n) over d times O(n) d cubed, which is equal to O(n) squared d squared. Now we deal with the second type of transitions. In order to do the second type of transitions in a more efficient way, we need a faster way to do the max plus product. To do this, we use another property of the similarity matrices, which is only true in the unweighted case. The similarity matrices are bounded difference matrices, meaning that the difference between the adjacent entries are no greater than 2. This is because if we look at the adjacent entries, they correspond to subforests that differ by at most one node. For bounded difference matrices, Freeman, Guendoni, Shasha, and Wasilewska-Williams showed in FOCS 2016 that the max product between bounded difference matrices can be done in O(n) to 2.8244 times, which is truly subcubic. In our paper, we extended to similarity matrices, and we showed that the max product of the similarity matrices S of f1 and S of f2 can be computed in O(n) squared, mean the size of f1 plus the size of f2 to 0.9038 times. So what does this have to say for the total time for all second type of transitions? If instead the maximal product took O(n) squared times the mean, the size of F1, the size of F2 instead, then the overall running time will be exactly cubic. Therefore, the speed up from cubic is equal to O(n) times mean, the size of F1, the size of F2, to 0.0952. In the analysis of our paper, we can somehow assume that mean, the size of F1, the size of F2 is omega d. And therefore, the improvement factor is at least omega d to 0.0952. And our total running time is therefore cubic divided by this improvement factor, which is O(n) cubed divided by d to 0.0952. Therefore, the total running time is O(n) squared d squared plus n cubed divided by d to 0.0952. We can set d to be equal to approximately n to 0.4773. And this gives us the final running time of O(n) to 2.9546. This concludes my talk. Thank you.